So we're looking at extended power rule, implicit differentiation and logarithmic differentiation, right? So let us begin with the extended power rule. In extended power rule, it is more of where we apply the chain rule, and when we have function, with that we have a power, right? So for y equals to fx to the power n, right? So in this case, first of all, we will be dealing with the power on top. So what we do is we put the function as it is at its place. We first bring the power in front of that function, which is n, and then we do n minus 1, that is minus 1 to the power. Now, you must have seen that we are leaving the inside function as it is, and then we multiply by the differential of the inside function. I hope this is clear. That's about extended power rule. So if given us with this example, how are we going to solve? This is again an example of extended power rule. So let's try to solve this particular question and see what will be the solution. So it says that y equals to x cubed minus 2 to the power negative 3. Now we can see that x cubed minus 2 is an inside power, and inside function, and there is a power on top. So what are we going to do is we're going to do dy over dx, which is equals to, what are we going to do? We multiply the power in front, which is negative 3, and as the rule says, we're going to leave the inside function as it is. So x to the power 3 minus 2, that's my inside function, but my power will change here, which will be negative 3 minus 1 will be minus to the power minus 4. Then the rule says we're going to multiply by the differential of the inside function, which is, if I differentiate x cubed minus 2, what do I get? 3x to the power 2, and for minus 2 this will become 0, because when we differentiate a constant we get 0. So that will be the answer for this particular question. Is it clear to you, or do you have any confusion? Okay, good. And now let us look at derivative of exponential. So when we differentiate a function where we have an exponential, where we have e to the power x, when we differentiate, we get e to the power x. So there is nothing that has been changing here. Alright? Make sense? Right, so what we normally doing is, what is actually happening, why do we have e to the power x here is, because we are going to differentiate the function on the top, right, and whatever we get, we multiply in front here, and then we put e to the power x as it is. So when we differentiate x, what do we get? 1. So in this case, 1 does not matter a lot. So say for example, if you have a function if you have a function f of x equals to e to the power let's say 2x, right? You're going to differentiate this. Now in this formula over here, we have e to the power x, but now that we have 2 in front. So when I do f dash of x, what am I doing exactly is, when I do this, what do I have to do? I have to take the differential of this. So I have to differentiate the power. If I differentiate 2x, what do I get? 2. So I will multiply the 2 in front, and then I will leave multiply by e to the power 2x as it is. So whatever the function over here is, I will leave it as it is, but what I'm doing is I'm going to differentiate the power. Whatever I get as the answer, I put it in front. Make sense? This is how we differentiate functions with exponential. Is it clear? Or is there anything that you... Okay. Now when we differentiate ln, which is logarithms, right? When we differentiate ln x, we get 1 over x. Now how are you getting 1 over x? It's very simple. Whenever we differentiate ln of f of x, whatever the differential of f of x, it will be on top, and we divide by the original fx here. So same thing applies here. When we differentiate x, we get 1. So 1 is on top, and then we have to put the original function as it is. So if I now say that fx is equals to ln x squared, that's your function. So what will be your f dash of x in this case? My f dash of x, as per what's been given here, I have to put the f dash of x on top, and then I have to divide by the original function. So what is my fx here? X squared, right? So if I differentiate x squared, what do I get? 2x. And then I divide by the original equation, which is x to the power 2. Is it clear? Or there is any doubt? Is it clear? Are you confused about something? Okay. So that's this. Now, when do we use a rule of implicit differentiation? You must have heard about the differentiating using implicit, implicit differentiation. This is where you have x and y both combined. There you will not be able to make y the subject of the formula to some extent, right? So here it says an equation that can be solved for one variable in terms of the other is called an explicit relation or function. So up till now, whatever functions that we have been differentiating is explicit, right? Because we always get a function in terms of y equals to something or fx equals to something. But now the case will be different. For implicit relation, we will have something like this, y squared plus x squared equals to 1. Or we can even have xy plus y squared plus x equals to 2. So in that case, it will not be easy for you to make y or a is the subject of the formula, right? So if you come up with a situation like that, then that's when we're going to use implicit differentiation. So for good? You getting me? Good. So, if first step is to know whether that equation is in terms of one variable equals to something or not. If not, then we have to apply implicit. Now, another thing is, what do we have to do? Now we have to treat y as an unknown differentiable function of x and differentiate both the sides of the equation with respect to x. So whatever that we are differentiating, we have to differentiate in terms of x. Now we have to solve equation for dy over dx. Now there is very important note that we have to keep in mind is whenever we differentiate y, we have to put dy over dx. So if say for example you are differentiating x squared, y squared. So in that case, you will do 2y multiplied by dy over dx. So keep that in mind, make that as a note that whenever we differentiate y in implicit differentiation, we have to put dy over dx. It's a must. Right? So we will be looking at some examples later on. Right. Now this is logarithmic differentiation. What do we have to do? As the name suggests, logarithmic. So we will be applying ln. Right? So technique useful for differentiating functions composed of products, quotients, and powers. So if we have if we have function which is composed of products, quotients, and power, it will be very useful for us to use logarithmic differentiation. It will be easy, right? Now, before going on to solving logarithmic differentiation, you should first know the laws, or what do we call, the rules of logarithms, right? So you should first know the rules of logarithms, which is, say for example, if you have, right, so if it would be ln x to the power n. So for ln, the rule says that in ln the power will come in front, right? So it would be n ln x. That's how it works, right? In ln, your power will get multiplied in front. I hope that you must be knowing about all these. Then if you have ln xy, when we have multiplication, we have ln x plus ln y, isn't it? When there is a multiplication, then we apply ln, we do plus, addition, right? So, and then if we have ln x over y, then if there is a division, then what do? We do ln x minus ln y. So far good? So these are some of the rules that you will have to remember in order to solve for logarithmic differentiation. So now let us look at some of the examples of implicit differentiation and logarithmic differentiation, right? Just give me a minute. So let us look at the examples over here. Is it readable? Can you read it properly? Okay. So this is the particular question or a function that is given to us, where it says that we have to differentiate x squared minus 5xy plus 3y squared equals to 7. Now just by looking at this particular equation, what should come in your mind? Which method will you use to differentiate this particular equation, or the function, sorry? Which method will you use? Implicit, yes, because you can see, that there is a y multiplied here, there is a y squared here, whereby it will be hard for us to make y the subject of the formula, right? So, and whenever we differentiate y, we have to multiply by dy over dx. That's what you need to keep in mind. Now let's start looking at how it's been solved. So for x squared here, we are going to differentiate that first. We have 2x, right? I think that should be clear. Minus, now 5x into y. Okay, can you see two functions being multiplied here? X is a separate function and y is a separate function. So, or we can treat it as a fx, 5x as one function and y as another function. So in this case, we will use which rule? If we have two functions multiplied, which rule will we use? Any idea? Yes, product rule. Very good. So we will be using product rule here. So we treat 5x as fx and we treat y as gx. Now, first of all, we will differentiate y. So putting 5x as it is, so we have 5x. Then if I differentiate y, I should get 1. But differentiating y, we have to put dy over dx. Then we do plus. Now I have to differentiate, 5 will remain as it is. 5. Now I have to differentiate x. Differentiating x will give me 1. And then I have to leave my y as it is. So far good? Is this part clear? This differential of using product rule. Now after this, we have to differentiate 3y squared. Now when I differentiate 3y squared, I will have 3 times 2 which is 6. Y. Then since I am differentiating y, so I have to write dy over dx, which is equals to, you want me to repeat the product rule part, this part. Okay, so we have a function as 5xy, right? You want we have 5xy. Now, since two functions have been multiplied together, which is x and y, I have to use product rule. Right? So, product rule says that, so we assume that this is my fx and this is my gx. So, it would be fx multiplied by g dash of x plus dx multiplied by f dash of x, right? This is the formula. Now, first of all, I will put fx as it is, which is I will leave 5x as it is, multiplied by, now when I differentiate y, what should I get? 1. So, it will be 1, but since I am differentiating y, so I have to write dy over dx because I am differentiating y in terms of x. Plus, now my gx will be, this 5 is just a constant that has been multiplied, right? So, this 5 will remain as it is. So, it would be 5y multiplied by, now if I differentiate x, I should get 1. Or we can say that even if you treat that 5xy as 5x is one function and y is another, so when we do this, gy, your y will remain as it is. Then you can do f dash of x will be, if I differentiate 5x, I should get 5. So if I further simplify this, I should get 5x dy over dx plus 5y. Hope this makes sense. Is it clear now? Okay. So that was the product rule. And we have stopped here. And this 7 will become 0 because differentiating a constant gives us 0. Now we will further simplify this. There is a minus here. So what we will do is we will multiply that minus 2 the variables inside. So it will be 2x minus 5x dy over dx. So plus and minus will become minus 5y plus 6y dy over dx, which is equals to 0. Now our task is to bring all the variables with the dy over dx one side, and then bring those without the dy over dx to the other side, right? Because our task is to form an equation whereby we have dy over dx equals to something. That is our task, right? So here we will do, since we have negative 5x with dy over dx and 6y with dy over dx, so what we will do is we can take dy over dx common out here, and then we will put minus 5x plus 6y, which is equals to, now I will bring those without dy over dx on the other side, which is 2x. If I'll take it on the other side, it will be negative 2x. And if I take negative 5y on the other side, it will be plus 5y. Now what I have to do is I have to make dy over dx subject of the formula. So I will have dy over dx here. I can take this particular part on the other side. It will be negative 2x plus 5y divided by negative 5x plus 6y. Now, even if you will leave your answer here, it is correct. And if you want to further simplify it, then you can change the signs here. So this minus will become plus. And if you will make these as plus, so this will become minus. And this is plus, so that will become minus. So for good, or any confusion there? If this part is confusing, just leave it. Right? Even if you won't change the sign, they won't mark you down, because this is the correct answer. So good? Okay. So now let's look at one example of a logarithmic differentiation. So the problem is we have to use logarithmic differentiation to differentiate y equals to sin x to the power 6x. So remember one thing, they will ask you to use logarithmic differentiation to differentiate a function which will be given in this form, right? Something like this. So first of all, what you have to do is you have to apply ln both the sides, right? So what you're basically doing here is you are doing this. Since you have y equals to sin x to the power 6x, so you're doing ln y equals ln sin x to the power 6x. This is the first step, right? This is the first step. Then later on, you know that log rule says that if we have a power, we have to bring that power in front of ln, right? So we will have ln y equals to, now I'm going to bring 6x in front, then I will have ln sin x. This is what is being given here, right? So first part will be this, you just apply ln and then you bring that 6x in front. Is this part clear? Is it clear? Okay, good. So now whenever we differentiate ln of something, what did I tell you? The differential part will come on top and the original function will go in the denominator. Right. So, and there's another thing which is very important that I told you is whenever we differentiate y, we have to multiply by dy over dx. Is it okay? So, Now if I have given ln y, if I differentiate, I'll get 1 over y dy over dx. Then, now can you see this 6x is one equation on its own, right? And it is one function, and ln sin x is another function. So now there are two functions multiplied together. So in this case, which function will you use? Which rule will you use? Product rule, isn't it? Yes. So again, we will be applying our product rule. So what will happen is, first of all, we will differentiate this 6x. Now, for product rule, it depends. You can either differentiate fx first or gx, because there's a plus, so it won't matter. It will still give you this right answer, right? So if I have 6x, so I have to differentiate 6x first, that would be 6, and I have to leave gx as it is. So in this case, that's my fx, and this is my gx. Right? So I differentiate the 6x first, which is 6, and I have to leave my gx as it is, which is ln sin x. Now, differentiating sign will give us cos, right? You have to know all this. So differentiating sin x, we get cos. So as per ln rule, the differential part will be on top, and the original function, which is sin x, will be in the denominator. Then we multiply by fx, which is 6x. So now you simply have to make dy over dx the subject of the formula. So in making dy over dx subject of the formula, you are required to take this y on the other side, right? So which would be, since there is 1 over y here, if I take this y on the other side, it will be multiplied, right? And this will remain as it is inside. Now, we cannot put anything in terms of y on this side. So what I have to do is, I have to substitute my y back, because my original y is sin x to the power 6x. So I will change it back. So for good, and this part will come from top, it will follow up. So that's how logarithmic differentiation works. Is there any question? So now, let's look at the last example over here. Okay, you're most welcome. So now we have to solve this particular question, right? We have ln y equals to half ln. Okay, I think I have started with the solution already. Okay, this is the question. Sorry for that. This is the question given to you, which is y equals to root or x cubed secant 5x. That's the original question given to you. Now what is the first step? What is the first step? You have to apply ln both this side. Right? You have to remember all these. Break it down into parts. It will be very easy to follow, and you will never end up making a mistake. So first step is you apply ln both this side. So it will be ln of y equals to ln, or now instead of root, we know that root is same as writing to the power half. So what I can write is x to the power 3 multiplied by secant 5x. This whole thing will be to the power half. So for good, I hope this is clear. Good. So now I will leave ln y as it is here. Now the rule says for ln that we have to bring the power in front. Good. So we bring half in front and then we leave ln and then we have x to the power 3 and then we have secant 5x. So for good, what I did is I brought the power this half in front because that's what the rule says. Now there is another rule for logarithm, which is when you multiply, when there is a multiplication, what do? See, there is x cubed, which is multiplied by secant 5x. So what do you do in this case? Is there any rule for ln which we can apply here? Okay. So at the moment we are not differentiating, right? We are just simplifying it. Simplify applying the log rules. I hope that makes sense. Right? We have not yet started with the differentiation because we have to check for all the log rules which we can apply before we actually start differentiating. So another rule for log ln is when there is two functions multiplied, we separate them with the addition sign, isn't it? So that would be 1 over 2. Then we have ln x to the power 3 plus ln secant 5x, isn't it? So that was it. Did you understand what we have just done? So here it says the same thing, whatever we did. We brought the half in front, then we put ln x cubed secant fx as it is, then we do half, and then we have to separate by the addition. Now you are at a position to differentiate this particular equation because all those rules which we could apply for log, we have applied. We cannot further simplify this. Now you are ready to differentiate. So first of all, we start with the ln y. Whenever we have ln of y, we do 1 over y dy over dx. As simple as that. Now half will remain as it is. That's a constant multiplied in front. We start with this particular equation where it says 3 ln x. So 3 is a constant multiplied. We put 3 as it is. Differentiating ln x gives us 1 over x. So for good, is it making sense? Okay, good. Then, so this part is done, right? This part is already done. Now we just have to consider about ln secant 5x. So what are we going to do here? Now, you can see there's a function which is secant and there's one more function inside it. Isn't it? So what are we going to do first? So if I have to differentiate, if I have to do ln secant 5x, so for ln, the rule says that the differential part will be on top and the original equation will go in the denominator, right? So when I differentiate secant 5x, yes. So when I differentiate secant, I'm just talking about secant for now, right? Because see, there is a function inside it, 5x, which we have to treat later on. So here we are going to apply the chain rule. So if I differentiate secant, I should get secant x 10x. right? But in case of x here, we have 5x. So what are we going to do is secant 5x times 10 5x. So this particular part is just differential of secant. So this should be x, but instead of x, we have 5x. So we will put 5x, 5x. Now we will go and multiply this 5x. We will go and differentiate this 5x, which is 5. So this is how we differentiate this particular function. I hope this is clear. Because in this case, we will be applying the product rule. But there is something that I am missing, which is divided by the original function, which is secant 5x. So for good? So that's how we differentiate this. Now, we can cancel this secant 5x with this secant 5x because they have been divided. Like here, we can cancel these two. And we will be left with, so here, now I have, now this half has been multiplied, so I can do 3 over 2x plus, now I have 5, 10, 5x. This whole thing will be now multiplied by y because I have to bring this y from here to here. And then I have to substitute my y back. That's the answer. So I hope that you're clear with the concepts today, whatever that we have covered. And today we have covered two major types of differentiation, which is implicit and logarithmic. And there's a high likely chances that it can be asked in your exam. So I recommend you that you learn it thoroughly. Practice as many questions as you can, because that's how you learn, like that's how you master yourself in maths. So that's it for today. I hope that you enjoyed the session, and I'm looking forward to see you next week.